Well, the topic of this lesson is least squares approximation. And as usual, we start with a problem statement. I try to explain where this method, where and when this method can be applied. Let's consider some real-life problem. From the physics, we know that Hooke's law states that when a force is applied to a spring, then the length the length of the spring is a linear function of that force. If the force is zero, then the spring has some length. If we apply some force to the spring, then the length is increased. So we can write the linear function f of L that equals to k times L minus E, where f of L is a force required to stretch the spring L units. E is the length of the spring with no force applied, and k is some constant. So it means that if L equals to E, that force equals to 0. And suppose that we want to determine the spring constant for a spring that has their initial length 5.3. We apply forces of 2, 4, and 6 and find that its length increased to 7.0, 9.4, and 12.3. So we have 4 points. When the force is 0, their initial length is 5.3, this point. When the force is 2, the length is 7. Force is 4, the length is 9.4. 6, the length is 12.3. And these points do not quite lie in a straight line. And the goal, the task is to find some line that is the best approximation to these points, that best approximates all the data points to determine the constant. And this type of approximation will be considered in this lecture. So again, from the mathematical point of view, the problem is as follows. We have a set of points. We know that these points must lie at a straight line, but they do not quite lie in this line. This point, for example, little bit higher, this point a little bit lower. No such line that passes through all the points. But we are trying to find some line that passes somewhere near all of these points. that approximates these points on some best way. In approximation theory, there are two general types of problems. One problem arises when a function is given explicitly, but we wish to find a simpler type of function, such as polynomial, that can be used to determine approximate values of given function. In this case, we know the formula for the function, but this formula is very complex. Maybe it includes a lot of sinus, cosine, exponential function, logarithm, and we want to approximate this complex function with a more simple function. Because polynomial is a simple function and it's very simple to compute the value of a polynomial. And the other problem is related with the fitting functions to given data and finding the best function in a certain class of the functions to represent the data. So in this case, in the second case, we have a set of points, a given data, and we want to find the best, in some sense, function that approximates these data in some best way. And both of these problems have been considered in previous lectures. For example, the Taylor polynomial or Taylor series of degree n about the number x0 is excellent approximation to n plus 1 times differentiable function f of x in some small neighborhood of x0. We will use the we used this type of approximation when we derive the formulas for numerical differentiation or numerical integration. To derive such formulas, we take some point x0 and we write a function, we write a Taylor series, and we take several first terms from this series, and we consider this polynomial as approximation to a function f of x in some small neighborhood of the point x0. This is the first case. And the second case is an interpolating polynomial. We consider two types of interpolating polynomials, Lagrange and Newton interpolating polynomials. And both of these polynomials of degree n can be used as an approximating polynomial and as polynomial to fit their given data. But now we consider the problem of finding the best function in a certain class of functions to represent the given data. Again, let's consider some set of points. And suppose that these points come for us from some experiment. So these points correspond to some experimental data. When x equals to 1, y equals to 1.3, x equals to y equals to 3.5, and so on. We have 10 points. The last point is 10, and the value y at this point is 15.6. So this picture illustrates this point. And you can see that these points lie somewhere near some line. So, and from this graph, it appears that the actual relationship between x and y is linear. And the likely reason that no line precisely fits the data is because of errors in our experiment. But of course, these points doesn't correspond to x square, x cube, or sinus, or logarithm. It's a linear function, but these points lies somewhere near this line. This point is below the line, this point is maybe a little bit higher than the line, and our goal is to find this line. And usually it is unreasonable to require that the approximating function agree exactly with the data. It means that it's not very good that approximating function pass exactly at each point. In fact, such a function would introduce oscillations that were not originally present. Let's look to the next picture. On this graph, the same points are placed. As you see, this point is 1 and 1.3, and the last point is 10 and 15.6. But it's just another scale. And situation is the same. These points lies somewhere near the line, but we can try to find interpolating polynomial that interpolates this data. We have 10 points. There are 10 points. Using these 10 points, we can build 9th degree interpolating polynomial. And on this picture, the graph of this 9th degree interpolating polynomial is shown. And you see that this polynomial passes exactly through all of these points, but at this end, at the end, this polynomial lies somewhere rather far from the points, the imaginary points between these two points. So the line, some line, will be the better estimator to this data in comparison with the 9th degree polynomial. The interpolating polynomial is clearly a poor predictor of information between a number of data points. So between these data points, polynomial is a good predictor, but between these data points, this polynomial is bad. is a poor predictor. A better approach would be to find the best in some sense. We discuss a bit about it later. What is the meaning of the word best? Approximating line, even if it does not agree precisely with the data at any point. It means even this line doesn't pass exactly through all of these points, because of course there is no line that can pass through all of these points. And when we talk about the line, when I tell that to find the line, what does it mean? What is the meaning of the words find the line? I just want to just type here a formula. What is the formula of line? What is the formula of line? Sorry. Line, if f of x is linear function, it means that I should fix two coefficients, a0 and a1. This is the equation of line. F of x equals to a0 plus a1. And to find a line means to find the coefficients a0 and a1. If somebody tell me these coefficients, I can say, okay, this is a line, but this line is not a good predictor for this data. For example, this line can pass somewhere here or here. It's not a good predictor. And the task is to select the coefficients a0 and a1 on such a way that this line becomes a good predictor for the given data. Well, the initial information for our method, for this method, is a table of the values x and y. We know the points x, we know the value y. And we can compute the value of the line at this point. Not compute, but we can write. Of course, we don't know the equation of line. We don't know it, but because we don't know the coefficients. But I can write something like this. F of xi, so the value of the line at the point xi, so let me write it as L of x, because f of x is our initial function and L of x is a line that that we consider as approximation. L of xi equals to a0 plus a1 xi. And let a1 xi plus a0 denote the eth value of approximating line. And yi is the eth given value of the function. And the problem of finding the equation of the best linear approximation in the absolute sense requires that the values of a0 and a1 be found to minimize the absolute error. The largest error between yi and L of xi, a1 xi plus a0. So we minimize the maximum error. This is commonly called a minimax problem, but this problem cannot be solved by elementary techniques. I can write it, but I cannot solve it. Another approach to determine the best linear approximation involves finding the values of a0 and a1 to minimize the sum of the errors. Let's denote it as E1 of a0 and a1. If somebody gives me their coefficients a0 and a1, I can compute this sum because xi and yi are given data. And this quantity is called the absolute deviation. And the task is to find such a0 and a1 that minimize the absolute deviation. From the mathematical analysis, we know that to minimize a function of two variables, we need to set its partial derivatives to 0 and simultaneously solve the resulting equations. In the case of absolute deviation, we need to find a0 and a1. So we must, to do it, we must find their partial derivatives derivative of a0 and a1, and we need to set these partial derivatives to 0 and solve the system of equations for a0 and a1. But in this case, we have another difficulty, that the absolute value function, the module, is not differentiable at 0. And we may not be able to find solutions to this pair of equations. The situation is the same. I can write this function to minimize. I can write the system of equations that should be solved, but I cannot solve it because the absolute value function is not differentiable. Well, so I mentioned these two approaches, the min-max approach and absolute deviation approach, just to stress that the term best linear function can be considered, the best linear function can be defined from the different points of view, different approaches. But the most popular and the best from the computational point of view approach is called least squares approach. The least squares approach to this problem involves determine the best approximating line when the error involved is the sum of the squares of the differences between y values of approximating line and the given y values. Well, what is the difference between these two formulas? In this formula, we compute the difference between yi and L of xi. It's very simple. Let me just retype this formula. Just the error, just to stress, the error equals to sum, the sum from I equals to 1, I equals to, here it's written 10, but usually it's number of points, let it be m, number of points. And here I must write the difference, the absolute value, the difference between the real value of a function yi and our approximation L of x at the point I. But L of xi equals to a0 plus a1 xi. This difference may be negative, may be positive. And to compute the error, it's better to consider not just the difference, but the absolute value of this difference. And as I told you, this problem cannot be solved. But when we consider not the absolute value, but the square of this difference, this problem becomes solvable. Let's consider not the absolute error, but here, delete. But let's consider the sum of the squares of the difference at the point xi of the given function value and the value of a line that approximates this function. If I substitute the equation of line here, this formula becomes like is written in my presentation. yi minus a0 plus a1 xi. And this error is called least squares error. Least squares, it means that we compute the sum of the squares and we must minimize this sum of the squares. The least squares method is the most convenient procedure for determining the best linear approximations. Because the minimax approach generally assigns too much weight to a bit of data that is badly in error, whereas the absolute deviation method does not give sufficient weight to a point that is considerably out of line with the approximation. And the least squares approach puts substantially more weight on a point that is out of line with the rest of the data, but will not allow that point to completely dominate the approximation. Well, how to find the coefficients a0 and a1 that minimize this function? The general problem of finding the best least squares line to a collection of data points x0, xi, yi. So suppose that we have m points, m given points that are numbered from 1 to m. This general problem involves minimizing the error that can be computed using this formula with respect to parameters a0 and a1. Let me repeat again. X and y, xi and yi here are fixed points, are given points. And we are going to find the coefficients a0 and a1. So a0 and a1 are variables, are parameters for minimization. And for a minimum to occur, we need to compute the partial derivatives of this function, and we need to set these derivatives to 0. And after that, we should solve the corresponding system of equations for a0 and a1. We need to compute the partial derivative. This partial derivative is computed here. And this is a partial derivative dE for dA1. This partial derivative is given here. We set these partial derivatives to 0. And after that, we should solve the system of equations for a1 and a0. After some simplifications, this system of equations can be written in the following form. A0 times m plus a1 sum of xi equals to sum of yi. This is the first equation, and the second equation is a0 sum of xi plus a1 sum of xi in square equals to sum of the products xi times yi. This is a very simple system of equations. Two equations with two unknowns. Unknowns here are a0 and a1. M is number of data points. X are x values of data points. Y are y values of data points. To build this system of equations, we need to know M. We need to compute sum of x's. As you see, sum of x's is used here 2 times. As this coefficient and this coefficients, sum of y, sum of x square, and sum of the products xi, yi. Well, I hope that you remember how to solve systems of linear equations. In this particular case, this system is very simple. Just two equations with two unknowns. And we can apply here Gauss method to solve these equations, Gauss elimination method, or we can apply so-called Cramer rule to solve this equation, any method that you want. So you can type in Google system of linear equations. You can find here a lot of examples for system of linear equations, and maybe the more simple method is Gauss elimination method. Okay, you can find here another method that can be applied only for small system of equations is a so-called Cramer rule. You can find their examples of a Cramer rule for this very simple case with the system of equation with two equations and two unknowns. And particular this case, we have here two equations and two unknowns. And in this case, the formulas for A0 and A1 can be written explicitly. So this is this formula for the first unknown, this formula for the second unknown. As you see, I just apply here that Cramer rule to find A0 and A1. Okay, in any case, we can solve this system of equations. We can find A0 and A1. And after that, we can find the line. We can find the line that approximates the given data. Let's look to the first example. Let me come back to this slide. So these points are from this example. 1 is 1.3, 10 is 15.6. To apply this method, I should know, first of all, the number of points. We have here 10 points. Then I should know the sum of x's, sum of y, sum of x squared. This column corresponds to x squared. Yeah. This is sum of x squared and sum of the products xi times yi. Well, if we compute these values, after that we can just substitute it to this formula or to this system of equations, and after that we can solve it. And we can find the coefficients A0 and A1. Well, this is the answer. A0 equals to minus 0.36, A1 equals to 1.538. This answer is given with three digits after decimal point. So the line, the polynomial of the first degree that approximates the given data, can be written as follows. This line will be approximator to this data. And this is a picture. This is a picture that on this graph you can see the data points and the line. And you see that this line passes somewhere near the points. This point is upper, this point is below. This point is upper, this point is below. Some of these points can lie at a certain line. Sorry, you should answer. Okay, I'm sorry, I should answer the phone. Well, this picture, you can see the points and you can see the line that approximates this point. And the approximate values given by the line is written here in this table. This is x, this is y, this is real values, and these values are the values of the polynomial of the first degree of the line, p of xi. And you see that in this case, this sum of the squares, sum of the difference between real value and approximated value is 2.34. And this value, this error, is the minimum error. No line can give us smaller error. This line is the best. The best in a least square sense. Well, let me show you the concrete example. I skip all this. Let's consider these points Suppose that we have very simple points 1, 2, 3, 4 as x and 1, 2, 4, 4 as y. You see that as far as we have here two points with the same value, we cannot draw a line. We cannot find an equation of line that passes through all of the points. But we can find the least squares. The line that passes near these points in some least squares mean. I show you how to solve this problem in Microsoft Excel. What should we do? We should build this table. We should build this table. X, Y, X square, and xi, yi. We should compute these values. And after that, we should substitute these values into these formulas and find the coefficients a0 and a1. I already do it, and I show you the result. This is x. This column corresponds to x. 1, 2, 3, 4. And the last is sum. The last row is sum of x's. 1, 2, 3, 4, and sum of x's. Y. 1, 2, 4, 4. And sum of y. Well, according to this approach, what should we do next? We should compute x squared. This column corresponds to x squared. I just use the formulas in Microsoft Excel. B times B, B3 times B3, and so on. This is x squared and sum of x squares. And the product x times y. And sum of y's. I have these values. And after that I can compute the coefficients a0 and a1. As far as this system of equations is very simple, we have just two equations with two unknowns. I can apply Cramer rule. I can use these formulas. And I can apply this formula. This is a formula to compute the value of a0. I just type it in Excel. Only the constant I use here 4. 4 is a number of points. I have 4 points. And here the formula to compute y. Sorry, not y, a1. A1. Well, this is a0 and a1. And you see that their graph of the line passes somewhere near given points. This point is below, this point is below, this point is up the line, this point is below. Well, and on this picture, I want to show you very important feature of the least squares method. This column corresponds to the approximated value, p of x. How to compute it? X times a1 plus a0. I type the formula in Excel to compute the values. Well, and there is a very important feature that the sum of the approximated values will be exactly the same as sum of the real values. You see that the real values, the values of the function, are 1, 2, 4, 4, and approximated values are 1.1, 2.2, 3.3, 4.4. But the sum of the values is the same. Moreover, if we compute the error means the difference between real value and approximation. What is the error at the first point? Real value minus approximation, minus 1.1. We consider here the error, not the absolute value, but the error. Error at this point, 2 minus 2.2, minus 0.2. At this point, 4 minus 3.3, 0.7. And the last point, 4 minus 4.4 minus 0.4. And you see that the sum of the errors is 0. Why? It's a property, it's a feature of least squares method. Some error is negative, some error is positive, and the sum of the errors will be exactly 0. In this case, the beta indicator is not the error, but error in square. This column corresponds to error in square. The error in square is 0.01, 0.04, and so on. And the sum of the squares of the error is 0.7. Well, let me change the initial data. Suppose that I change the value of y here and I put here 4. What does it? It means that at this point the value will be 4. 4, 4, and 4. This point will move here. Let's look to what happens. Our line move up. Of course, these points are not very likely that these points lies in a straight line. But this line approximates these points on the best way. Because, again, the sum of the values, the sum of the real values equals to the sum of the approximated values. sum of the error is 0, and we have some non-zero sum of the squares of the errors. Well, is it more or less clear how to find the least squares line? Do you have any questions about it?
For me, no, Professor.
No questions. Okay, try to, as a homework, I will send you this presentation. Try to take these data, or you can change it, or you can take these data and try to apply this approach by yourself. Try to find the least squares line for this given data. Well, we have a few minutes, and in these few minutes, I want to show you just in a few words the general approach. Just a few words about the general approach. Because right now we consider a particular case, least squares line. But can we build a least squares polynomial of degree 2, least squares polynomial of degree 3? The answer is yes. Yes, we can do it. And the general problem of approximating a given set of data, xi, yi, with their algebraic polynomial of degree n, using the least squares method, is handled in a similar way. Let me repeat again. The question to find a polynomial is similar to the question to find n+1 coefficients of the polynomial. an -1, and so on, a1, a0. From this point of view, the polynomial of degree 0 is just a partial case of polynomial of degree n, p1 of x, right? So we choose the constants a0, a1, an to minimize the least squares error. Sum of the errors yi minus pn of xi in square. And after some simplifications, I skip it. Usually I describe these simplifications on the board, but now we have an online lesson. I cannot describe it. I cannot write it on the board. And the situation is exactly the same. We should find the partial derivatives dE over dAj, and these partial derivatives gives us n+1 normal equations for n+1 unknowns. And these system of normal equations have a unique solution, provided that their values of x's are distinct. And this is a system of equations in general form. The lower index I corresponds to number of points. The upper is a power. What is xi power 0? what is, it's a general question for you. If we consider any number power 0, x power, yes, it's 1.
It's
So,
one.
1, right. It's a very simple question, I hope, for you. X power 0 is 1. So this first sum is just the sum of ones. Sum of ones, it means 1 plus 1 plus 1 plus 1 m times. So this first sum is just m. And it's written here, a0 times m. The second sum is sum of x's. Sum of x's power 1. Right? The second sum, the next sum is sum of x squares. And so, suppose we are going to find the least squares polynomial of degree 2. So we need to interrupt this process here. And we should compute sum of x power 0. It's sum of ones, m. Sum of x, sum of x's, sum of x squares. Then, the next equation, a0 sum of x's, a1 times sum of x squares plus a2 sum of x power 3 equals to sum of y I x power 1. The next equation will be sum of x squares plus a1 sum of x power 3 plus a2 x power 4. Remember that we discussed about the case when n equals 2. So the last term will be x power 4 equals to sum of yix power n power 2. Well, and for example, for this given data, this data is also typed here in this example. So some other data is given an example. For suppose that we have this table of data, there are 5 points. There are we have 5 x's and 5 values of y. And to apply this approach, we should compute sum of x's, sum of x squares, sum of y's, sum of x power times y, sum of x times y square, and we can build this system of equations. We will have 3 equations and 3 unknowns. The unknowns are a0, a1, a2, the coefficients of the polynomial. And you see that this system will have the same coefficients here. 5, then 2.5, 2.5, here 1.875, 1.875, and these coefficients is also repeated. When we solve this system using Gaussian elimination, we find their values for a0, a1, and a2. And this is a polynomial of degree 2 that approximates this given data. Well, The main point from this lecture for you is to understand how to find a least squares line. The formulas for this method is given here. Also, you can find the squares method, least squares it's of course it's a very general formulation. It's formulated in a general form. Yeah, but you can find here this example with a line that approximates this given data and a quadratic polynomial that approximates a given data. Of course, maybe this page in Wikipedia will be hard to read for you because the least squares method is formulated here in general form. But you can find more information on other sites. The main information you can find it here in this presentation. Well, that's all for today's lesson. Next week, I hope we will meet in usual form, in a mixed mode, in class and in Microsoft Teams. And the last topic will be related with the numerical solving of differential equations. That's all. If you have any questions, you are welcome. If you don't have any questions, let me stop recording